This session will talk about user chemicals in CHEMCAD. As you see on the slide, we've got the word components. In CHEMCAD, we often use the word component when we're talking about chemicals. In this session, we're going to look at chemical components in the database. We're going to see how you can look at the properties that we're using for chemicals. We'll talk about how you can add your own chemical to our database. You might have a chemical that we don't have. So we'll look at how different ways you can add that chemical and talk about the different things you'll want to do, the different steps you'll do as part of making the new chemical. We'll also take a look at user databases for chemicals, how you can manage different user databases and how you can move chemicals between them. We're going to go over and we'll start a new simulation. I'm going to start a simulation. I'm going to put the chemical phenanthrene in the simulation list. I'm doing this because we will create multiple copies of a chemical based on phenanthrene, and we will be looking at them in the simulation. If I specify a stream and put phenanthrene in this stream, we can see various physical properties. So I'll specify this is at 70 degrees Fahrenheit, 15 pounds of pressure, and that we have 100 pounds per hour of phenanthrene. Now, when we look at the physical properties for this stream, we see that CHEMCAD has many different properties. We've calculated the density of this stream. We've calculated the volumetric flow. We display the critical temperature and critical pressure. We see the liquid heat capacity. We see the Z factor. Where do these numbers come from? Let's take a look in the database. If I go to Thermophysical menu, Component Database, I can view edit chemicals in our database. I'm going to find phenanthrene. Now we're looking at the View Edit Component data screen for phenanthrene. We could select another chemical, or we can look at the different properties of this chemical. So in the database for phenanthrene, we have a CAS number. Formulas, we have the overall formula. If we look at the minimum required data, as the name implies, this is the minimum data that you need to use a chemical in a simulation. That's if you want to use the chemical as a vapor liquid. From this information and the boiling point, we can predict many properties. We can correlate many properties. If we look at the basic data page, this shows us basic pure component constant properties. These are values that do not change with temperature. We see that the database entry for phenanthrene has most of these values. Where do these numbers come from? We'll talk about that in a moment after we look at temperature-dependent properties. Some of these buttons are for properties that we recognize as temperature-dependent. Density is a function of temperature. Vapor pressure and heat of vaporization are functions of temperature. Heat capacity and viscosity, thermal conductivity and surface tension are properties of temperature. Let's take a look at the density data screen. Here we see equation number 105, and coefficients. We see a low and high temperature range. What's that mean? If we look into the help, we'll be able to see equation 105. In the help, we see this is equation 105. That's how ChemCAD calculates density for phenanthrene at a given temperature. We take the A, B, C, and D parameters, we take the temperature, we use this equation to calculate the density. The low and high temperature, that's telling us the temperature range these parameters are valid for use. So where does this data come from? Chemstations is a licensed distributor of the DIPPER database. The majority of data in ChemCAD for pure components comes from DIPPER. Some chemicals in ChemCAD we've entered ourselves. Some chemicals use information that heat transfer vendors have provided. If we look at the other tabs here, these are different properties. We'll talk about UNIFAC group data later in this session. Other data and electrolyte data tends to be specialized values. Other data is specialized values that are not used by many methods or many equations. They're not a very basic pure component property. If we look through the temperature-dependent properties, we'll see that for phenanthrene, we have coefficients and equations for these properties. Phenanthrene is a very well-defined chemical in ChemCAD. This is a chemical that does come from the DIPPER database. So when we look at the stream properties for this stream, those properties are calculated using these equations. That's how we can look at a chemical in the database. Now let's take a look at different methods to add chemicals to the database. We're going to make our own version of phenanthrene with different methods. We're going to make our own version of phenanthrene because that will help us see the difference of what data is calculated by different methods. I'm going to go to Create New Component. And we have several different options for making a new chemical in ChemCAD. When we change correlations, you'll see that the required information is changing. We'll start with pseudo component. I'll give this a name, pseudo phenan. That will make it easier for us to compare all of the different chemicals. Now we know the boiling point and molecular weight for phenanthrene. These are not difficult properties to measure. So let's start with just that information. Let's say that we know the molecular weight, and we can get that from different sources. You can do it by test, or sometimes if you go to webbook.nist.gov, you can find a chemical you're interested in. Webbook says the molecular weight is 178.23. Boiling point is a fairly simple test. So let's enter this new chemical as though it is something that our chemists have had a little bit of time with. They were able to do a molecular weight measurement. They calculated that molecular weight is 128.2. They were able to do a boiling point test. They determined that the boiling point is approximately 645 degrees Fahrenheit. If we have a specific gravity or API gravity, ChemCAD can do a little more predicting power. These are both fairly simple to measure. Measure the specific gravity and you can back calculate the API. So let's say that our chemists tell us the specific gravity is 0.956. When we press OK, CHEMCAD is going to use this information to make a new chemical. It's going to use a number of different correlations. The name of this method is pseudocomponent. That's because this is a method that you would use if you were trying to make hydrocarbon pseudocomponents that are matching a distillation curve, like a D86, a TBP, a D1160. These methods tend to work decently for simple straight alkanes. CHEMCAD asks, where would I like to save this chemical? Right now, by default, there's a single database, user components. We'll talk more about databases in a later section of this webinar. So for now, I press OK. We've just created a chemical, so CHEMCAD is showing us everything it knows about this chemical. If we look at synonyms, CHEMCAD does not know the CAS number. Yeah, we could enter the CAS number. We could enter different synonyms. If we look at formulas, there's no formula here. We told CHEMCAD that we have a molecular weight, a boiling point, and a specific gravity. That's not enough information to determine a formula. That is enough information to come up with a rough guess for an N-alkane formula, but we don't know if this is an N-alkane. Actually, looking at the picture, I think it's safe to say that this is not an N-alkane. Yeah, if we enter the formula, CHEMCAD will use it to check if we have the correct molecular weight. If we look at the minimum required data page, we do have the minimum required data. This is information that was predicted by the hydrocarbon correlation methods. If we look at the basic data, we don't have as much basic data. The phenanthrene chemical had melting point, heat of fusion, dipole. It had ideal gas heat of formation and Gibbs of formation. If we start looking through the temperature-dependent property screens, we see blank values. The blank values are letting you know that CHEMCAD does not have a value entered here. So what does CHEMCAD do? Well, let's put this in a stream on the flow sheet, and then we'll talk about what it does when we run into blanks. We'll also be looking at the different methods, and we'll talk about what you should be doing after you make a new chemical. So we'll specify a new stream, and we're just going to have this be the same composition, but we want the new phenanthrene. So first I need to put it in my chemical list. So I'm going to select components. At the end, I find pseudophenanthrene. At the beginning, we have ID numbers. Old versions of CHEMCAD used a 4-digit ID number for chemicals. We don't do that anymore. For our chemicals, we still show the number because some users have them memorized. If you've been using CHEMCAD for a long time, you know that component 62 is water, 46 is carbon dioxide, maybe a handful of others. The source, this is showing us where the chemicals are coming from. Our chemicals are the system database. This user chemical is coming from the user components database. Okay, so if we get back into those streams, we can copy, and we'll change this to be a flow of the pseudophenanthrene. The relative enthalpy has changed. We have different heat capacities, so there's relative enthalpies. If the negative sign here bothers you for enthalpy, I'd ask you to look in the help under relative enthalpy, absolute enthalpy. You can also find a topic about that on our website at the Support Center. If we look at the stream properties reports for both of these streams, one of them has density parameters for the equation, and one of them doesn't. There's a little bit of difference on density here. I'm not going to say if this is good or bad, because it depends on your application. If you're using phenanthrene and you need to have microvolume accuracy, this would be a bad fit. If you're using phenanthrene and you care about barrel accuracy, this might be a good fit. The point is the numbers are different. Phenanthrene is being calculated, the density is being calculated by a temperature-dependent equation, which comes from experimental data. The Dipper group looks at experimental data, they look at predicted data, they look at related chemicals, and they use their vast experience to determine what are the best chemical parameters for this chemical. So I would have a degree of confidence in the density of the phenanthrene stream here, provided that I am operating within the temperature range for the density correlation. The pseudophenanthrene, the predicted chemical, we do not have density parameters. This is being predicted by different predictive methods. This density is going to be predicted from the specific gravity of the chemical and the boiling point, the critical properties as well. That is not a very accurate predictive method. If you want to know more about predictive methods for properties of chemicals, I strongly recommend the books Properties of Gases and Liquids. This has been a wonderful textbook. I'd recommend having that nearby if you use a simulator and new chemicals. I would also recommend Gmailin's new book on process simulator thermodynamics. If you take a look at our blog, one of the entries is books you should have on your bookshelf. So when CHEMCAD is missing temperature-dependent parameters for an equation, it will use predictive methods. We leave the values in the database blank because we want you to know we are predicting methods here. We'll talk about how you can take experimental data and improve this chemical after we take a look at the other predictive methods for new components. So I'm going to go back and make another new chemical. I'm going to choose the Joback method, and we'll call this Job Phenanth. The Joback method and the Unifac method, which should really be called the Leiterson method here, these are subgroup methods. With the subgroup method, researchers looked at a number of chemicals that we do know about, and they said, let's look at chemicals we know about. Let's identify functional groups that repeat. Right? This functional group repeats several times on phenanthrene. And we have a second functional group. So lost my color there. Yeah, so we have this functional group repeating several times. This is an aromatic with one hydrogen. We also have this functional group repeating several times on phenanthrene, an aromatic with no hydrogen. Researchers looked at chemicals that we know about, benzene, methane, ethanol. They identified the different functional groups, and they created regression algorithms to determine how much does a group like this add to the boiling point of a chemical based on the chemicals we know about. So when we're using a subgroup method, we're telling CHEMCAD what are the functional groups, and it's trying to make a prediction for some, and I emphasize the word some, of the chemical properties based on those chemical groups. So if we start with jobphenanth, I gave a specific gravity to the other chemical, so we'll give it here. This is optional, but this will give you slightly better results. So I'll give a specific gravity. We had the boiling point. I'm going to leave the boiling point blank this time. That would give us a better result. I'd like to see what happens if we leave it blank. But it's optional for the group contribution method. When we press OK, here are the subgroups that are published by Kevin Joback's paper. Kevin Joback's dissertation was an improved method for predicting pure component properties, boiling point, critical properties from the groups that are present. Yeah, for phenanthrene, we have, and I'm going to double check, I don't want to make a mistake specifying this. We have 4 groups that are an aromatic with no hydrogen. So we're looking for ring hydrocarbon. We have 4 of these subgroups. Looking at the drawing, that's 1, 2, 3, 4 of those subgroups. The other subgroup we have is an aromatic with 1 hydrogen. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these. And typically I'll do my drawing like this. I'll look at a drawing and I will mark it with pencil or with highlighter to identify the subgroups. That way I'm careful not to double count. Yep. So we have 10. Thank you. That's right. Actually, I've made a mistake. Yeah, we have 10 with hydrogen attached and 4 with no hydrogen. We press OK. It saves it to our user database. Let's take a look at the properties now. Formulas, we left that blank. The reason we left that blank is sometimes you're improvising with a Joback group. Sometimes you're trying to get close. You may have noticed that the Joback subgroups do not cover all the chemicals we know about. They do not cover all the elements we know about. If we look at the minimum required data, we've got the minimum required data. Basic data, we have slightly different numbers. With the subgroup method, we are able to predict the ideal gas heat of formation and the ideal gas Gibbs of formation. We're also able to predict solubility parameter. We have a predicted boiling point. So from subgroups, we're predicting a boiling point of 601 degrees. From our first chemical, you may recall the boiling point of phenanthrene is 645 degrees. So we see there's a bit of accuracy being lost here. If we look at the temperature-dependent properties, again, we have empty fields for the coefficients to calculate a temperature-dependent property. So let's put this chemical on the flow sheet and see how it compares with the other two. And I'll copy the flow of 1. Again, I need to add the chemical to my simulation. If you find yourself at AICHE meetings, Kevin Joback is actually a regular attendee at the exhibit booths, and he's a regular presenter as well as a member of several divisions. So yeah, stop by, say hi, tell him that you used his methods. All right, so we've specified a flow of the new Joback phenanthrene in the last stream, and we're going to compare the stream properties again. So we see some differences. We see that the critical temperature is different for each of these chemicals. We see that the liquid density is different. The two predicted chemicals are very close. I'll be honest, that's because I gave CHEMCAD the specific gravity for both of those chemicals. If I did not give it the specific gravity, I would expect that these two would be further apart. Okay, let's make a new chemical. This time I will leave the specific gravity unspecified. We can see how much different that might be. So we're going to go and we're going to do group contribution UNIFAC. I'm going to type LYD because this is really based off of the Lighterson method. You'll see UNIFAC in two different places in CHEMCAD. UNIFAC for vapor-liquid equilibrium and UNIFAC for creating a new chemical. These are not the same research groups. The Lighterson group noticed that the UNIFAC subgroups for vapor-liquid equilibrium were very useful, and they made a subgroup method using those subgroups. Okay, I press OK, and we see here are the Lighterson subgroups based on the UNIFAC models. You see that we have more subgroups for the Lighterson method than we do for the Joback method. And we'll find we have 10 ACH, and for A, here the A is letting you know aromatic ring member. We press OK. We'll save the chemical to our database. And we look formulas. We're still leaving that blank in case you wanted to do something unusual. We've had people where they have all but one of the chemicals, all but one of the elements they want, they can use a subgroup method to predict. Sometimes people will use that as a starting point, and then they'll adjust the chemical information. That's why we leave the formulas blank. Minimum required data. We have minimum required data. Now some of you may have noticed that each of these methods has different number of coefficients for the polynomial ideal gas heat capacity. Each of these methods is also going to have a different result for calculated ideal gas heat capacity. If we look at the basic data, again we have a subgroup method. It's able to predict heat of formation and Gibbs of formation based on the chemical structure. If we look at the temperature-dependent properties, these fields are still blank. We'll put this in a flow sheet and we'll see how this compares with the others. And remember, we did not tell CHEMCAD a specific gravity for this chemical. So I expect that the density of this stream will be less accurate. All right, so we look at the report for each of these streams. And we'll start with density. It's interesting. The density is actually more accurate for this. Stream number 4 is the Lighterson method. I can put labels on these streams. That would make this easier to see. we'll label these database, pseudo, Joback, and Lighterson. Yeah, so if we look at the densities, not having a specific gravity gave us a better actual density. Why? Well, this is where it might be interesting to look in a book like Properties of Gases. If you look at the discussion on predicting density, you'll see that the methods that the pseudo component uses are methods that you would use for very simple alkanes, the type of thing you might find in a mixture of components in a crude. The Lighterson and Joback method, the subgroup methods, can predict density based on the structure. So even though we did not give it the specific gravity, Lighterson able to make a better prediction just from what other densities looked like. And the Lighterson method is really predicting a specific gravity to use. If we look at some of the other properties, critical temperature and critical pressure. The pseudo-component method has a very large error on this critical pressure. The Joback method and the Lighterson method both have some error, not as much as the pseudo-component. Okay, so we've looked at how we can do a basic prediction of chemicals. We've seen that when we do a prediction of pure chemicals, we're missing data. CHEMCAD, unfortunately, does not magically know all the properties of a chemical based on the name of the chemical and the boiling points and maybe the structure. Eventually, thermodynamicists and physical chemists will give us very strong methods to predict any chemical, but the research isn't there yet. These methods tend to be more accurate the simpler and more alkane-like your chemical is. You'll see discussion that the Joback method is considered within 15% for a simple straight alkane. This is not a simple straight alkane, so we might have a larger error. How accurate is CHEMCAD's prediction using these methods going to be? We simply don't know. You would have to compare the results of the predictive method with experimental data to know how accurate it is. My recommendation, if you're dealing with a chemical that has any complication to its structure, anything more complicated than a simple alkane, tell CHEMCAD more about the chemical. Let's see how we could do that. Let's talk about density. That's probably the easiest property. We're going to take some experimental data for density and improve the CHEMCAD's prediction. I'm going to go to the thermophysical menu, component database, component property regression. I'm going to do a regression for liquid density of pseudophenanthrene. So I need to press new, liquid density. I need to give this a name, experimental data. Comments. We had 3 quick measurements. These are just notes that I can see in the simulation in the future. CHEMCAD starts by showing us the equation it's going to use by default for regressing density. This is the equation that Dipper recommends. This equation tends to do better extrapolating beyond temperature of data than other equation forms. Let's say that we have 3 quick measurements from the lab. we have a measurement at 40 degrees, 70.1. For density, we have a measurement at 70 degrees of 70 pounds per cubic feet. And we've got a measurement at 120 degrees of 68.5 pounds per cubic feet. Now I'm doing 3 data points because this is a quick example of how to do a property regression. That does not mean 3 data points is enough to get a good curve. Maybe it is. Maybe it's not. It is not. I perform the regression. Now in the background, we'll look at in the background first. This is a report from the regression. The regression has converged. We see at each temperature what was the input value and what was the calculated value. Looking at these numbers, I consider this to be a fairly accurate fit to my data points. We also see the parameters CHEMCAD is going to use for the density of this chemical. Now we have a dialogue with a very long question. Yeah, I'm sorry, we found that we really do need to use this much length when we're showing it to you visually. When you're listening to me, it's much easier to tell you what we're doing. We just regressed properties for this chemical. Do you want us to use this for this chemical everywhere that you have it? Do you want us to put these changes in the simulation where you specified the chemical and also in your user database? In most cases, the answer is going to be yes. So in most cases, you will use the default. Yep, you use the changes and put the changes in the database. The other option, it's a really advanced case. The other option would be you want to use the chemicals in you want to use the changes in other simulations, but not this one. So let's just stick with what is the default. The default option, we just performed a regression. We're going to use the new parameters in this simulation, and we're going to save it to the database. We get a question from CHEMCAD about reinitialization. We just changed a chemical property. CHEMCAD wants to know if it should recalculate the physical properties of every stream. I'm going to tell it, yes, I want you to recalculate all of the streams on the flow sheet using the database because I just made a change to density. CHEMCAD shows us the data points versus the predicted curve. Looking at the numbers, I thought it's a great fit. Looking at the plot, I think maybe it's not that great a fit. I think maybe one of these 2 data points is questionable. Which one? I don't know. I only have 3 data points. That's not enough to start guessing if there's a bad data point or if there's something unusual. Okay, so we're back in CHEMCAD. Let's look at the stream property report that we've been looking at several times. If we view properties, if we look at the actual density, now I changed the actual density for the pseudo. So we see the pseudo is very close to the database value. If you're wondering where I got those experimental values from, you may have just guessed. I took 3 different temperature points, and I took a little bit of random change at 3rd decimal point. So the 3 data points we have are based on the actual density from this curve. Let's take a look in the database, and I'll show you a shortcut. If we press the component list button here on the command bar, that shows us a list of chemicals that are in the database, and we can double-click on one to view edit. Now I mentioned that CHEMCAD does not use 4-digit ID numbers anymore. When you look at a user chemical, you will see an 8,000 number. That's something ChemCAD is internally doing at the simulation. If you started using ChemCAD with ChemCAD 6, don't worry about this number. If you're watching this and you used ChemCAD 5 or ChemCAD 4, you might be thinking that you've found the secret way to use the 8,000 numbers. No, you haven't. Please don't assume that pseudophenanthrene is always 8001. The first user chemical is called 8001 in this simulation. So if you're a new user of ChemCAD starting with version 6 or later, don't worry anything I've said about the 8000 number. If you're a legacy customer, thank you, and give us a call to talk about that number before you try and do anything creative. So we're looking at pseudophenanthrene. On the density data, now we've coefficients specified. Because we regressed data, ChemCAD filled this form out, and it put in a low val and a high val on temperature based on what our coefficients were. Now the high value and the low value here, these are calculated from the parameters and the temperature. If you are manually entering values here, you can come back to the screen and you can see what are the calculated low and high values. That's a quick way for you to check, did you make a typing mistake? Okay, so we've taken a look at how you can create a new chemical, and we've looked at how you can start to regress data for the chemical. We can also look at this data in visual form. At the flow sheet, I can go to the plot menu, stream properties. This is a pure chemical stream. If I plot, I'll use Jobac. I'm going to plot the density of Jobac, that using plot menu, stream properties. So I'm going to plot the liquid density from 100 to 600 degrees with 30 data points. Yeah, I used the plot menu and plotted stream properties. So ChemCAD is showing me the density of that stream at different conditions. I can also go into the database and I can say I want to plot properties from the database for select components. Or I could find phenanthrene here. I could say I want to see the liquid density from 100 to 600. If I do that command, I get a blank screen. The plot command inside of the database menus is going to plot what does ChemCAD have stored in the database. The plot menu command for stream properties will show you what are the properties ChemCAD is going to use based on your thermodynamic settings for this stream. So this is showing us the predicted values. Occasionally there's a difference between a predicted value on the stream and what's in the database, because the thermodynamic settings might be calling for a different value. Yeah, for example, if you use an equation of state for enthalpy, plot menu command for stream of the liquid heat capacity will show you a value calculated by the equation of state. The plot command within the database will show you the plot of the liquid heat capacity stored in the database. So we've looked at different ways to specify chemicals and talked about how you can improve a chemical. One other thing we're going to talk about is database management. If I go to thermophysical menu, component database, manage databases, this is where we'll see the user database your computer is connected to. By default, we create this database, usercomponents.ppdb, and we're going to put it in your My Documents folder. I'm logged in as a user CHEMCAD, so I see it in Users CHEMCAD Documents. You'll see a different path here, but the default will be in My Documents, My Simulations. We put an empty database so you have a single database to start. You can have multiple databases. I could create another database. I could create a database for a project. Let's imagine that I'm working for a famous fast food restaurant company. And I'm not going to use I'm not even going to use a name because who knows what you can be sued for these days. So let's say that I have a database called Fast Food Restaurant. When I make a new chemical now, I can choose the database. So I'm going to go to New Chemical. We'll create a new component. I'm going to give a name Ketchup. And no, I don't. Actually, let's give a name Thousand Island. A name Thousand Island. And this may or may not be the secret ingredient to my sauce for one of my sandwiches. If I give a boiling point, I'm just making a guess. Now I can choose to put that chemical in the database Fast Food Restaurant. If I have a coworker who's using the same chemical, who wants to use my chemical, if I have a coworker on the same project, I can share that database with him and he will have my copy of the chemical. If I put that chemical in the simulation, when I put a chemical in the simulation, CHEMCAD will store a local copy in this simulation. If I send this simulation to you, when you open this simulation, you'll be told there are local chemicals, pseudophenanth, jobdurant-phenanth, light-phenanth, and Thousand Island. Do you want to save them into a user database? You can say no. You can leave the user chemicals inside the simulation, or you could import them to your own database. I'm going to go back to the Manage Database screen for a moment. Some good practices here. If you have several coworkers and you have chemicals where you want an official version, I recommend creating a database on the network. I also recommend that you ask IT to restrict write permission. Let all the CHEMCAD users read that location on the network, but only allow one of them to have the computer privilege to change the database. Elect an official database manager who is the person responsible for changing the values in the official database on the network. I would also suggest if you have different projects for different customers, consider making a different database for the official version of the project for that different customer. If you're a consulting group, this is an easy way to separate confidential data for that customer. You could put the database, it does not need to be in your documents folder. You could put it in the folder which is clearly named confidential. If you get a database from someone else, or if you know a network location, you can come and you can press connect. And you can point to the location of a database. And you could select a database to connect to it. When you're done working on a database, you can disconnect. Disconnecting does not delete the database. It only removes the connection on this computer. Import is really for importing legacy values from old CHEMCAD 5 simulations. we do have the ability to import a neutral file, which is a special text file. The neutral file is a text file with special keywords that you could use to build information that you have for a chemical. If you're trying to migrate a chemical database into CHEMCAD, the neutral file import might be useful for you. Give us a call about that. Kevin Jobek's software, Cranium, it has the ability to export to the CHEMCAD neutral file import. So if you're a user of his software, which has advanced property prediction methods, you could export the chemical and then come over to CHEMCAD and import it. So to sum up what we've done, we've looked at how you can view chemical components in the database. We talked about where the data comes from. We talked about how you can create a new chemical. We looked at 3 ways to accomplish this. There are 2 other methods on that menu that I did not mention. The Electrolytes method is for very special situations. If you are trying to add a new ion for an electrolyte reaction, you might use the new component method electrolytes. And I would really ask that you call to talk with us, because adding a new electrolyte reaction is a fairly advanced topic. The solid combustion would be useful if you have something that you want to burn in a reactor and you have the heating value. If you have a coal in elemental analysis and the high or low heating value, you'd use that method. Those are the methods we didn't talk about before. But we talked about 3 main methods: the pseudo-component method, the Jobek subgroup method, and the Lyderson subgroup method. We talked about how you can add data to the chemical to improve what CHEMCAD knows for that chemical. And then we looked at database management. We talked about how you can store chemicals, how you can connect to different databases. On the component database menu, there are commands for move and copy. You can copy chemicals from one database to another. We also talked about how and when you might want to share component databases between users. So I'd like to thank you for taking time to listen to this CHEMCAD Essentials webinar. At this point, we're finished with the webinar. We're going to take time if there are any questions from the audience. All right, I'd like to thank Wendy Reed, who's working in the background here, for identifying some questions that we need to bring in front of everyone. Question number 1, can you create a user-defined mixture which has well-known thermodata individually? An example would be air. What you can do, and what you'll sometimes see in CHEMCAD, you can make a new chemical and you can take the data which is known for that mixture and you can regress it to a chemical. I'll go over to CHEMCAD and I'll look at some examples. Like in the database, we have a chemical called air. Personally, I almost never use this. If you have reactors, please do not use the chemical air. But the chemical air represents a 79-21 approximate mixture of nitrogen and oxygen. And the different properties were regressed from property tables versus temperature. We have a number of refrigerants in the database, like Freon 290. A number of refrigerants are entered as a pure chemical based on the mixture properties. In reality, many of these refrigerants are not mixtures. They are in reality, a number of these chemicals are mixtures. They are not pure chemicals. It's often easier to do a single chemical that has properties based on the mixture. So yes, you can quickly enter a single chemical and give it data from a table for a mixture. Okay, another question we have, if you're using a subgroup method, how do you decide which subgroups to use? For example, you might be able to use a single subgroup, CH2COO, or you could use two different subgroups, CH2 and COO. Which should you use? In general, when you're using a subgroup method, try to use the largest subgroup possible. That will give you the most accurate results. If you've talked with me on the phone or in person, you've heard me use the analogy of Legos. A subgroup method is like making a Lego sculpture in reverse. A subgroup method says there are frequently occurring patterns. Let's figure out the contribution for those patterns and predict the properties. That's kind of like saying we know what a Lego spaceship looks like, and we know the different Lego parts that are used to make a spaceship. Now we're talking about something else. We're talking about a Lego dinosaur. Now subgroup method would be like saying, let's take the Lego components that we know about and throw them all into a pile, and we're going to claim it looks like a dinosaur. If you're talking about a very round dinosaur, it might look like a dinosaur. If you're using larger subgroups, if you use subgroups that are 50 Lego pieces stuck together, your pile of Lego subgroups might look more like a dinosaur. So in general, if you're using a subgroup method and you see different possible subgroups, try to choose the largest subgroups.